In this video, we're going to talk a little bit about trigonometric substitution and how that can help us integrate certain functions. So we apply trig sub when we have expressions like these in our integrand, this a squared plus x squared and a squared minus x squared. So for the purposes of this discussion, we'll only consider a squared plus x squared and a squared minus x squared, where a is just some real number. So if I have a squared plus x squared in my integrand, I want to let x equal tangent theta. Sorry, a times tangent theta. Not arctan, but a tan theta. Now, this implies by our mnemonic that dx will equal a times secant squared theta d theta. But what is important here is that if x is equal to a tan theta, I can draw a right triangle with angle theta. And I remember that tan theta is equal to my opposite side over my adjacent side. And I can solve this equation up here, x equals a tan theta, to get that tan theta equals x over a. So this tells me that I can write this triangle as having opposite length, this length here, x, and having adjacent length, that is this length here, as a. So my hypotenuse by the Pythagorean theorem, we'll say c squared, is equal to x squared plus a squared. That is, c is equal to the square root of x squared plus a squared. Now this will help us later when we need to get back in terms of x. Similarly, if we have a squared minus x squared, I want to let x equal a sine theta. Okay? Then again, I will have that dx equals a cosine theta. And additionally, I know that sine theta is equal to the opposite over the hypotenuse. So drawing my right triangle here that I'm talking about when I let x equal a sine theta, remember not arcsine, but a, where a is just some number, we can solve and say that sine theta is equal to x over a. So that tells me that my opposite side is going to be x and my hypotenuse is a. And like I did before using the Pythagorean theorem, I can find that this length here is going to be the square root. Oops. It's going to be the square root of a squared minus x squared. Now notice that, and this is a very interesting fact, the missing side is the square root of our original expression in both of these. Okay, just something interesting to note. So let's apply these facts to some integrals to kind of see why trigonometric substitution is useful. So looking at this first example here, I have the integral of 1 over the square root of 9 minus x squared. So I can rewrite, well, let's just think about this. So what I have in the integrand there, this part inside the square root, the radicand, it looks like a squared minus x squared. And in this case, a would be 3. So I'm going to let x equal 3 sine theta. And I'll go ahead and say now that this implies that dx is going to be 3 cosine theta d theta. Okay. Now, applying that substitution here into my integral, I have that this guy is the integral of 1 over the square root of 9 minus 3 sine theta squared, right, because x was 3 sine theta, and then my dx became 3 cosine theta d theta. So times 3 cosine theta d theta. Cool. So now I notice that this 3 sine theta squared is going to be 9 sine squared theta. So I'll go ahead and rewrite this here as the integral of 3 cosine theta over, so I just pop that 3 cosine theta on top, over the square root of 9 minus 9 sine squared theta d theta. Okay, now I'm going to pull this 9 out front here, but if I pull this 9 out, I have the square root of 9. which is 3. So I can rewrite this as, so I'll just highlight this step here. What I'm doing here is I have the square root of 9 minus 9 sine squared theta, and that's the square root of 9 times 1 minus sine squared theta, and that is 3 times the square root of 1 minus sine squared theta. So this is equal to the integral of 3 cosine theta over 3 times the square root of 1 minus sine squared theta d theta. Now from here, it's pretty easy to see that these 3's will cancel. And another thing to notice is that 1 minus sine squared theta is cosine squared theta. And the reason for that is we know that sine squared theta plus cosine squared theta equals 1. So subtracting sine squared theta from both sides, we get that cosine squared theta is equal to 1 minus sine squared theta. So applying that to this next step here and canceling out those 3's, I have that this is the integral of cosine theta over the square root of cosine squared theta d theta. Now this square root and the square will cancel, so I'm just left with the integral of cosine theta over cosine theta d theta, which is just the integral of 1 d theta. Now that just happens to be theta plus c. So now the question is, well, what is theta, right? I need to get back in terms of x because my original integral was talking in terms of x. Well, at the very beginning over here, we let x equal 3 sine theta. So we can solve this equation for theta to get what we should plug in for theta here. So I can show you that x equals 3 sine theta means that sine theta equals x over 3. And taking the inverse sine of both sides, we can see that theta is equal to arc sine of x over 3. This tells me that my entire integral here, which was originally the integral of 1 over the square root of 9 minus x squared dx, is equal to theta plus c, and we just solve for theta as arc sine of x over 3 plus c. Great. And if you know the formula for the integral of 1 over a squared minus x squared, you can verify very easily that this will give you arc sine x over 3. Okay, so now moving on to a slightly more complicated example. Let's go over here. So I have the integral of 3 over 7 plus x squared, quantity squared, dx. So I have something that resembles a squared plus x squared. And in this case, a squared is 7. So this means that a is going to be the square root of 7. So I'm going to let x equal a tan theta because I have this plus here. So it's going to be the square root of 7 times tangent of theta. Now very quickly I can see that dx is going to be equal to the square root of 7 times secant squared of theta d theta by taking the derivative. Okay, so let's go ahead and make our substitution here. So under our substitution we have that this is the integral of 3 over 7 plus the square root of 7 tan theta squared, and then my dx we solve for is the square root of 7 secant squared d theta. So I have times the square root of 7 secant squared theta d theta. Okay, rewriting here, I get the integral of 3 times the square root of 7 secant squared theta over 7 plus the square root of 7 tan theta squared is going to be 7 tan squared theta squared, and then d theta. So the fact I used in this step is that square root of 7 tan theta squared is 7 tan squared theta. Cool. Now, in this next step, I'm going to use the trigonometric identity that 1 plus tan squared theta is equal to secant squared theta. So I'm going to apply that in here. And then I guess it would be simpler for me to first pull out this 7. So I'll pull out this 7 right here. So working on this denominator here, I have 1 plus tan squared theta. So I can rewrite my integrand as the integral of, I'll go ahead and pull this 3 square roots of 7 out. So I have 3 square root 7 times the integral of secant squared theta over 7 times, remember 1 plus tangent squared is secant squared theta squared, right, because everything was being squared, and then d theta. Now again, I can rewrite as 3 square roots of 7 over 7, and then I have the secant squared up here, and I will have secant to the 4th down here because I have secant squared squared. So I have the integral of 1 over secant squared theta, d theta. And then this is just going to be 1 over secant squared. Recall that secant theta is 1 over cosine theta. So 1 over secant theta is equal to cosine theta. And the same is true if I square them. So 1 over secant squared theta is equal to cosine squared theta. Okay, so now we have cosine squared theta d theta. Now to compute this integral, I'm going to use the identity that cosine squared theta is equal to 1 plus cosine of 2 theta over 2. Okay, so this will give me, rewriting this, 3 square roots of 7 over 7 times the integral of, I can go ahead and break this sum up in the numerator, 1/2 cosine 2 theta d theta. Okay, so that's just me splitting up the sum into 1/2 and cosine of 2 theta there. Okay, next we can actually just go ahead and integrate here. So we're integrating with respect to theta, so I have 3 square roots of 7 over 7 times the integral of 1/2 is going to be theta over 2. And then plus, you can verify this pretty easily by a u substitution, that this is going to be 1/4 sine 2 theta, and then all plus c. So now the question is, we finished our integration, we're all done, but now what about these thetas? Okay, so we need to draw out our triangle to determine what's actually happening with x in terms of theta. So remember that at the very beginning, we let x equal the square root of 7 tan theta, okay? This tells us that tan theta is equal to x over the square root of 7, okay? Now I can draw a right triangle based on this with angle theta to determine what my other trig functions of theta are going to be. So I have tangent is opposite over adjacent. So my opposite side is x, my adjacent side is the square root of 7, and my hypotenuse is going to be the square root of x squared plus 7. And you can find that very easily by using the... Now, this doesn't help me quite yet, but we will get there. Another thing to notice is that if tan theta equals x over 7, sorry, x over the square root of 7, then theta is equal to arctan of x over the square root of 7, okay? So that'll help us substitute this lonely theta back in. So again, because I don't know what 2 theta is, if I want to substitute this this sine 2 theta back in terms of x, I know things about theta, the triangle that has, angle theta, the right triangle, but I don't know things about 2 theta, because it's not as simple as just multiplying things by 2. So I'm going to rewrite this using the identity that sine 2 theta is equal to 2 sine theta cosine theta. So that tells me that I have 3 square roots of 7 over 7 times theta over 2 plus 1/4 times 2 sine theta cosine theta plus c. Okay, now I can determine sine and cosine of theta based on this triangle by recalling that sine is just opposite over hypotenuse and cosine is just adjacent over hypotenuse, right? And then we already just saw that theta is that arctan here. So we can rewrite everything now in terms of x. So I'll have that this is 3 square roots of 7 over 7 times 1/2. Remember, theta is arctan x over the square root of 7, so arctan x over the square root of 7. And then plus 1/4 and a half will cancel out and give me, or sorry, 1/4 and 2 will cancel out and give me a half. So I have 1/2. And then sine theta we said is opposite over hypotenuse, so opposite over hypotenuse is x over the square root of x squared plus 7 times cosine, which is adjacent over hypotenuse, So that's the square root of 7 over x squared plus 7, the square root of that, and then plus c. So finally, rewriting everything, I have that this is going to be 3 times the square root of 7 over 14, arctan of x over the square root of 7, plus 3 square roots of 7 over 14 times, we'll just rewrite it. We'll write it all as one fraction. So I'll have 3 times 7, or we'll go ahead and write it this way. Square root of 7 times the square root of 7, because we're talking about this term here, so I have square root of 7, square root of 7, and then times x over 2 times 7 is 14 times, I have 2 copies of the square root of x squared plus 7, so I'll just be left with x squared plus 7. Similarly, these square roots will square and cancel out, so I'll be left with 7 plus c. So finally, rewriting this in its final form, I have 3 square roots of 7 over 14, arctan of x over the square root of 7, plus this 7 and a 7 from this 14 will cancel, so I'll have 3x over 2 times x squared plus 7 plus c. And that is our final answer. So notice how making that simple substitution up at the beginning, when we notice that we have something like a squared plus x squared, letting x equal square root of 7 tan theta, allowed us to integrate this integral that we wouldn't normally be able to do using the methods that we've previously learned. Okay, and it's very important to either know the identities to be able to rewrite things from theta to x, or to be able to draw this right triangle here using your identities. Another important step that I wanted to highlight is using the identity sine 2 theta equals 2 sine theta cosine theta. Because like I said, we don't know anything about 2 theta, but we know things about theta. So we want to get everything with just theta, okay? Now moving on, I wanted to show kind of an interesting example. We want to show that the derivative of arctan of x is 1 plus x squared. Okay, so this is something that's kind of just fed to you in Calculus 1. This is just a fact that's given to you maybe on a derivative table, that the derivative of arctan of x is 1 over 1 plus x squared. And it's kind of something that you're just told to memorize but not really given a reason for. And so here I'm going to kind of show why that is using trig sub. So to say that the derivative of arctan of x equals 1 over 1 plus x squared by the fundamental theorem of calculus is equivalent to stating that the integral of 1 over 1 plus x squared dx is equal to arctan. So to show this, we will show that the integral of 1 over 1 plus x squared dx is equal to arctan of x. Because from this, by the fundamental theorem of calculus, if I take the derivative of this, I obtain my original equation that the derivative of arctan is equal to 1 over 1 plus x squared. So we're just going to show that the integral of 1 over 1 plus x squared is equal to arctan of x. And how we're going to show that is by computing this integral using trigonometric substitution. So we'll let x equal, in this case, just 1 tan theta. So dx will equal secant squared theta d theta. Now under the substitution, my integral here, the integral of 1 over 1 plus x squared dx, I don't know why I'm having so much trouble saying that, becomes 1 over 1 plus tan squared theta, and then my dx became secant squared theta d theta. Recall that 1 plus tan squared theta is equal to secant squared theta. So this is equal to the integral of secant squared theta over secant squared theta d theta, which is just the integral of 1 d theta. And in this case, we're just looking at theta plus c. Okay, c being our constant of integration. So we need to solve for theta in terms of x because we were originally talking in the language of x and now we're in the language of theta, so we need to get back to the language of x. So when I let x equal tan theta, that gives me a relation that I can use to solve for theta. So if I take the arctan of both sides, theta is equal to the arctan of x. So this tells me that my entire integral was arctan of x plus c. So we just showed that the integral of 1 over 1 plus x squared dx is equal to arctan of x. And minus some technical details, this would suffice to show that the derivative of arctan of 1 over x is 1 plus x squared. And that kind of wraps up everything that I wanted to say about this topic. So if you found this video helpful, please consider liking and subscribing. Thanks.